Hello everybody. Today we're going to be talking about 4.3. This is monotonic functions and the first derivative test. So to start with, when we talk about monotonic, we're mainly talking about if a function is increasing or decreasing on the interval. And your corollary says, suppose that f is continuous on closed interval ab and differentiable on the open interval ab if, when you take your derivative f prime x, and if it's greater than 0 at every point, at each point, this means within, that fancy Greek E, within or belongs to, or is a member of, different ways to say the same thing. If x is a member of AB, or if x is within AB, then f would be increasing. So if your derivative is positive, then it's increasing. If it's negative, then it's decreasing. And then here's an example where they're telling you to identify the where it is continuous and differentiable for this example for a cubic function. And there's the function, the cubic function, and they break it up into two intervals. They find their zeros of the derivative at -2 and +2. How they did that is because if you have your x cubed, then on your derivative it's 3x squared. You have -12x, so your derivative is -12. And then your derivative of -5 would just be 0. So then this has a common factor of 3. You can factor out a 3 and get x squared minus 4. And then you'll end up splitting that up into the difference of two squares and setting these equal to 0, so you'll see why it's -2 and +2. So then, just by having those 2 points, you can say, well, to the left of this one, in the middle, or to the right. And so those are your 3 conditions. And what they're doing is they're just checking any value to the left of -2. They chose -3, they could have chosen -4 or whatever. But at that point they saw it was increasing because it's going up. And then for this one, a very good easy number to check would be 0. And it's decreasing at that point. And then on this one, they chose any number greater than 2. And in this case, they chose 3. They could have chosen 4, could have chosen 10. Anyway, it's increasing because it's going up. The next part is about the first derivative test for local extrema. So here they're just showing you all sorts of characteristics of this unique piecewise graph. You have an absolute minimum here because that's the lowest point throughout everything. And then this point where it's flat, where f prime is 0, would be no extremum. So that's not a minimum or a maximum. This would be a local maximum because it's a high point, but it's not the highest overall. Just within, here to here, or if you want to split up your interval, whatever. But it's not the absolute max like this one is. This one shows you a local minimum here. As I said a moment ago, this is the absolute max. Now in this case, it's undefined because although it's sort of like this, it's not smooth. It has a cusp. And remember, when we said that it has a cusp, it would be undefined. And again, this is just where it's changing direction, so it's no extremum, just like this other one. And then at this point, you have a local minimum. So that basically has all your conditions that we've talked about. Remember, f prime greater than 0 is when it's going up, and so it's going up here as well as here and there, and then it's decreasing here, here, and here. So those are your critical points. And then here's your first derivative test. If it goes from negative to positive, it's a minimum. Positive to negative, it's a maximum. If there's no sign change, there's no local extremum. But again, I would just use the graph and see where it's going up or down. Okay, our next example says find the critical points of this function, it's a cubic function. First thing you can notice about this is they have x to the 1/3 times x. They're distributing. And so they're treating the x like it were x to the 3/3. So then you go 1/3 plus 3/3 is 4/3. So that's how they get their x to the 4/3. And then they're also distributing x to the 1/3 times -4, and so they get -4x to the 1/3. Remember that x to the 1/3 is really like the cube root of x, but we just want to keep it in fraction form or rational form. The reason is because it'd be easier to do your derivative. So when we take our derivative of this, we put our fraction in front, then write the x, then decrease by a whole number. So you're going from 4/3 down to 1/3. Then you would take the derivative of x, but that's just 1. So the derivative of x to the 4/3 is 4/3 x to the 1/3. And then you have to take your derivative of this one. So you go 4 times 1/3 is 4/3. You keep your negative sign. And then you decrease by a whole power, like 1/3 minus 1, and you get -2/3. And so that really means move it below. Make it become the denominator. And so that's what they ended up doing. And then they looked at the graph. Based on the function, we knew the critical points were at 0 and 1, and so they're testing to the left of 0. Then between 0 and 1, like they might check a half or a third, just whatever works, and then anything to the right of 1. And so they can say decreasing, decreasing, increasing. And then the last example has to do with the trig function, but it's the same idea. So the main challenge on this part would be if you have sine squared, you're taking your derivative of that and you take your 2, put it in front, then your derivative of sine is cosine, and then you still have to keep the sine the way it was. So the derivative of sine squared is 2 sine cosine, and then the derivative of sine is cosine. Then they factored out a cosine. They put it in the back instead of the front, but it's the same idea. And then you were left with 2 sine x minus 1. So at that point, you set your derivative equal to 0, and that's sine x is a half, and cosine x is 0. So sine x is a half means y is a half, and that happens anywhere above the x-axis with the reference angle 30 degrees. And 30 degrees is the same thing as pi 6. So pi 6 and 5 pi 6, which is like 150 degrees. Then cosine is 0 where x is 0, and so that happens at the 90 degree place, which is pi halves, and the 270 degree place, which is 3 pi halves. And then they're showing you all your different intervals. So from 0 to pi 6, and then from pi 6 to pi halves, pi halves to 5 pi 6, 5 pi 6 to 3 pi halves, and then 3 pi halves to 2 pi. So one thing you may realize as you're doing these is if it's trig, you're going to have more intervals. You're not just going to have 3 intervals. And this was your function, and then they just showed you decreasing, increasing, decreasing, increasing, decreasing. So just graph your original function and then find your derivative and the key points, and then find out whether it's increasing or decreasing. Okay, so now we're going to go on to problems. It's numbers 1 and 3, and then 9 to 49 every other odd. So the first questions are asking about analyzing functions. What are the critical points? On what open intervals is it increasing or decreasing? And where are the local maximums and minimums? So your first question is x times x minus 1. Okay, so again, page 201, 1, 3, and then 9 to 49 every other odd. Okay, so number 1, on this one we have f prime of x is x times x minus 1. So part A is asking about the critical points. Part B is about the intervals, the open intervals for increasing and decreasing. And part C is about local max and min. So those are the 3 things we're going to look at for each equation. Okay, so for number 1, if we have f prime of x equal x and x minus 1, notice they've already done the derivative. Already did the derivative. And so what you want to do is set it equal to 0. So you're doing x times x minus 1 equals 0, so x is 0 and x is 1. So that's your critical points. So basically for your open intervals, we want to talk about happening at 0 and 1. What happens to the left, in between, and to the right. And so what we have to do is graph it. So we just want x times parentheses x minus 1. If you leave off the times, then it won't work. Actually, I'm going to show you that. If you do it this way, it says error cannot accept change, invalid input. So make sure when you're doing these that you put a little time sign right there. And it doesn't matter whether you're in degree or radian mode, since it's not trig. So what we notice is to the left of 0, it's decreasing. It's basically decreasing all the way here and then coming up here. Okay, So just to remind you, what we saw in the examples was when it graphed the original function, and if you graph the original function, if graphed f of x, which is not f prime, then visually see increasing and decreasing. But if you're given f prime, then substitute numbers. So basically, if you looked at the graph, you'd say decreasing, decreasing, increasing, but that's not right. So we need to try a number smaller than 0, and so we're going to try f prime of -1. So f prime of -1 would be -1 times -1 minus 1. So -1 times -2, which is +2. And so that's why we get a positive number. So I'm just going to put a little plus sign right here. And then between 0 and 1, we could say a half. I'm going to try positive 0.5. Decimals probably would be easier on this one. If you prefer using fractions, you can. So we're going a half times a half minus 1. So that'd be a half times negative a half, which is negative 0.25. So you get negative. The actual numbers don't really matter. You just need to know that you get a negative. But this was right. 0.5 minus 1 is negative 0.5, which is what goes in the inside, and multiply that by the 0.5, so you get negative 0.25. Okay, so then we just need to try something greater than 1, and so I'll try 2. So this would be 2 times 2 minus 1. So that's just 2 times 1, which is 2, so that's positive. So you have plus minus plus. Okay, so what we put for B is that we are increasing where you saw the pluses. So increasing on open parentheses, negative infinity 0, and 1 comma infinity, and it's decreasing on 0, 1. So put this part and this part for B. You don't have to necessarily write the middle part, which is your work for this one. Okay, then for the local max and min, we're going from positive to negative. And that's going to be a local maximum. You're going to have a local max at x equals 0 and a local minimum at x equal 1. Okay, so for C, we have a local max at x equals 0 since f prime is from positive to negative. And at 1, let's see, at 0 it was going from positive to negative. At 1 it's going from negative to positive. So this is since f prime is from negative to positive. Okay, so there's number 1, a really good example about that. Now we have number 3. Number 3 has the same instructions, but it has f prime of x equal x minus 1 squared times x plus 2. So again, it's already done the derivative. So for part A, we want the critical points. And so that would be at x equal positive 1 and x equal negative 2. Basically set each of those equal to 0 and solve. So those are your critical points. By the way, on the first one, make sure you write the original function too, the original derivative. So you get that, and then for your open intervals, we're going to have 1, we're going to have negative 2, and so basically we're going to try f prime of something to the left of negative 2. So let's just try negative 3. And then we're also going to try 0, which is in between negative 2 and 1. And we'll try 2. So these are going to be your 3 places we check. So when we plug in a -3, we go -3 minus 1 squared times -3 plus 2. And then the next one, well, let's go ahead and get that answer. Okay. Parentheses, -3 minus 1 squared times -3 plus 2. That gives you -16. So the main thing is it's negative, so you put a little minus here. And then at 0, we're going to get -1 squared times 2. And so that would be 2, which is positive. And for the next one, we're going to have 2 minus 1 squared times 2 plus 2. That just gets you 1 times 4, which is 4, which is also positive. So you have a minus plus plus. So what that means is you're going to go from negative to positive means you're increasing. So for this part, when you have negative infinity, -2, that's a minus sign, and so that was decreasing. And the other two are going to be increasing. So you're increasing on -2, 1, and 1 infinity, and you're decreasing on negative infinity to -2. So for part C, for your local max and min, we're going from negative to positive. And whenever we go from negative to positive, that's going to be a local min. And that's going to be at the -2. And there's no local maximum. Because we had positive and positive. So that's the end of number 3. On number 9, we have f prime of x equal 1 minus 4 over x squared, which is the same as this. Make sure you write the problem. What they're wanting you to do on this one is get a common denominator. Of x squared. And so f prime of x equal x squared. And since the 1 doesn't have an x squared, we need it. So it's x squared like that, because x squared times 1, and then they put minus 4. So that's your common denominator. So then what you want to do is set that equal to 0. So you have your x squared minus 4 equals 0. You're going to move your 4 over, then take your square root, so you do get plus and minus 2. And you also need x equals 0. Since it was an asymptote. Since the vertical asymptote. So what that means is your critical points for part A are x equal plus and minus 2 and 0. And then we need to do our drawing. And so then we're going to try f prime of negative 3, f prime of negative 1, f prime of 1, and f prime of 3. And so you have 4 places you need to check because there were 3 points. I went ahead and put negative 3 squared as positive 9. Remember, negative 3 times negative 3 is positive 9. So this gives you 5/9, and so that's positive. Now we're going to try negative 1, and so we have negative 1 squared minus 4 over positive 1. So that'd be negative 3. So since it's negative, we'll put a little minus there. Then this one would be positive 1 squared minus 4 over positive 1, and you still get negative 3, so negative. And then on this one you go positive 3 squared minus 4 over 9, which would then be positive 5/9. So you're basically going plus, minus, minus, plus. Our next step is to set up our intervals, negative infinity to negative 2, negative 2, 0, 0, 2, and 2, 0. So because it was a negative 2, we go negative infinity, negative 2, and then negative 2, 0, 0, 2. Then this should be 2 infinity and beyond. Okay, so this one you're going to increase because there's a plus, and on this one you're going to decrease because there's a minus. On this one you're also going to decrease. I'm just going to put it plus, minus, minus. And then on the last one you're increasing because it's plus. So basically, if you see a plus, then you put increase. If you see a minus, you put decrease. And then the next part is about your local min and max. So at -2, you go from positive to negative. At x equal -2, positive to negative. And we said when we go from positive to negative, it'd be a local max. And at 2, it's going from negative to positive. At x equal to negative to positive. So local min. Okay, so those are the first 3. I'll upload this video now and then start working on the next.